Okay, so we're going to continue on with the work from 8C, but now we're going to look at depreciation, which is an example of linear decay. You might remember from last year that depreciation is when an item loses value over time. So a classic example is a car. As soon as you drive it out of the car yard, it's no longer worth the $40,000 that you paid for it. In doing this, there's a few terms that we just need to know, which are listed here. So future value and scrap value. Future value is the likely value of an item after a certain amount of time, so predicting how much something would be worth in 5 years, whereas scrap value is when an item depreciates so far that it's now worthless. So then it's just like sold for scrap, for example, or it's disposed of at that point. Now, in terms of depreciation linearly, there's two types that we need to understand, and that is flat rate depreciation and then unit cost depreciation. Now, flat rate is when a constant amount is subtracted to decay the value of the asset over time. And again, now it uses this linear decay formula that we looked at earlier. So this is the formula here that we need to use. And once again, D gets calculated as being a rate times VO, but you'll notice in the formula that it's VN now minus D because that value is decreasing over time. So here we've got a question. It says that Sam purchases a new car for $40,000 and discovers that it depreciates by 15% of its purchase price each year. Model the depreciating value of the car with a recurrence relation. So once again, to get us started here, we need to find the size of D. So R over 100 times VO, in this case, 15% of $40,000. So calculator here, 15 over 100 times 40, 123, and that is $6,000. So if we write this now as a recurrence relation, VO, our principal in this case is $40,000. That was the initial price of the car. And VN plus 1 equals the previous value minus 6,000. So we can see that car value is decreasing really quite rapidly. Part B wants us to know how much the car is worth after 3 years. So again, we can then use that sort of sequence formula where we type in the initial amount of 40,000 and then type minus 6,000. So after 1 year, 34, 2 years, 28, 3 years, 22,000. So we can see there that after 3 years, like the car's practically halved in value. That's lost a lot of value. Part C now, it says the car is considered scrap when its value is less than $10,000. How long will that take? So if we keep pressing enter now and keep counting, I'm pressing it now for the 4th time. The 5th time it's at 10,000. Now this says when it's less than 10,000. So it's less than 10,000 after 6 years. Okay. So in this case now my answer is 6 years to be less than $10,000. So hasn't lasted long, that car. Finally for D, it says create a graph of the value of the car over time. I could do that in my calculator, or I could just set it up here. So if we set up my axes, your x-axis is always going to be the time, in this case in years. And so we've got 0, 1, 2, 3, 4, 5, 6. And this is our value of the car. So let's call this 40,000, 20,000, 10,000. That in there is 30. And that is car value. Now, initially the car was worth $40,000. We knew at year 3 it was 22,000, so I can put that dot in there. And I knew at year 5 it was 10, I can put that in here. And 6, it's then 6,000. And if you drew this up, you would have a nice even scale, and you would have a ruler, and you can draw those dots up. The point I wanted to make though with these graphs is before, when we looked at the simple interest graphs, I'm going to scroll out quickly. Remember, simple interest, it was adding on plus D. So we can see there that the line is sloping up from left to right, showing an increasing trend. But if we come back down to the one that we just drew when we were talking down here about decay, we can see that that line is sloping downwards from left to right because we've got that subtracting of 6,000 each time here. And it's forming a perfect straight line because we've got linear decay happening. Our second example here talks about unit cost depreciation, and unit cost depreciation is when the future value of an item is based upon its use rather than its age. So a classic example of this might be like a photocopy machine, and it is getting used by printing however many pages, and maybe after printing, I don't know, 50,000 pages, it's then lost its use. It's like down to scrap there or something. So again, we've got now this same sort of rule with minus D, but this time D represents the cost per unit of use. So it might be, say, 4 cents for every page that's printed. If we look at this example, we've got a new computer is purchased for $2,000 and it depreciates at a rate of $2.50 per day used. So again, we've got here VO is that 2,000 and $2.50 per day. This is our D amount, that cost per unit of use. So creating a recurrence relation then for part A, we're going to say that VO equals $2,000. And then Vn plus 1 is equal to Vn minus $2.50. Now, B, it says how much is the computer worth after 5 days of work. So 5 days is what we're trying to figure out. Remember, I mean, this one's quite easy. Small numbers. I could work this out in my head, but I could just pop it in here of 2,000 and then do minus 2.5 and now count 1, 2, 3, 4, 5. So after 5 days, the computer's worth $1,987.50. So it's lost $12.50 in value in those 5 days, which doesn't seem like much, but you can imagine how quickly then that will decrease. So that is a summary of 8C, looking at linear growth and decay in the realms of simple interest and then depreciation. The next video is going to build on this, looking at 8D, which is creating a rule for the nth term, still with linear growth and decay. So please click on to the next video to continue with 8D.